Since pulse oximetry was introduced 3 decades ago as a monitoring tool, it has become ubiquitous in operating rooms, intensive care units, and hospital wards. Before pulse oximetry was available, physicians relied on invasive procedures, such as arterial blood gas analysis, to identify the presence of hypoxemia. Pulse oximetry has now become the standard of care in operating rooms and intensive care units in the United States and many other nations. Although the pulse oximeter is easy to use, the clinician must understand the principles of pulse oximetry and must know how the equipment works in order to interpret the information it provides. This video demonstrates the equipment needed and how to use it. It also addresses the common applications of pulse oximetry, explains how to interpret the data generated, and presents its limitations as well as common problems encountered with its use. Oxygen is present in 2 forms in the blood, dissolved and bound to hemoglobin. Hemoglobin can be functional or non-functional in terms of oxygen binding and transport. Functional hemoglobin binds and transports oxygen and is present as oxyhemoglobin and deoxyhemoglobin. Oxyhemoglobin contains bound oxygen, and deoxyhemoglobin is reduced hemoglobin without bound oxygen. Non-functional hemoglobin is unable to bind or transport oxygen and is present as carboxyhemoglobin and methemoglobin. Carboxyhemoglobin is hemoglobin bound to carbon monoxide. Methemoglobin is hemoglobin that contains ferric iron, Fe3+, an oxidized form of the oxygen-carrying ferrous iron, Fe2+, which is found in functional hemoglobin. The partial pressure of oxygen dissolved in arterial blood is termed PaO2. The percent saturation of oxygen bound to hemoglobin in arterial blood is termed SaO2. When measured by a pulse oximeter, SaO2 is termed SpO2. The hemoglobin-oxygen dissociation curve shows the relation between PaO2 and SaO2. The affinity of hemoglobin for oxygen varies at different partial pressures of oxygen, and although the relation is not linear, increases in PaO2 lead to higher SaO2. In general, 80% saturation corresponds to a PaO2 of 50 millimeters of mercury, and 90% saturation corresponds to a PaO2 of 60 millimeters of mercury.